Hello everyone, welcome back. And in today's video, we're going to be covering the topic of virtual work to some problems. And at the end, I'm going to give you a homework problem from a recent AITS. So let's just begin by discussing what the method actually is. Okay guys, so first of all, what is the method of virtual work? So it states that if a rigid body is in equilibrium, okay, so this is important guys. So the body has to be in equilibrium. Then the total virtual work, which I'll tell you what that is, of the external forces acting on the rigid body is zero for any virtual displacement of the body. Okay, now what is virtual displacement and virtual work? Okay guys, so for that, pay attention to this image over here. Imagine we have a particle A over here and the particle A is in equilibrium, which means if I add up all the forces vectorially, I should get the answer as 0. Okay, so now the thing is, imagine in your head that we displaced it by a small amount of delta R. Okay, so it's called virtual because it's not a real displacement. We are not really displacing it. For the sake of imagination, we are imagining a displacement in our head, and that's why it's called virtual displacement. So again, we use the symbol of delta for representing it. Okay, I mean, you can use whatever symbol you want. As it is virtual, we are just using this symbol delta. Okay, so this delta R is nothing but the small microscopic virtual displacement. Let's say the work done by all the forces acting on the particle is represented by delta U, and this you can again write it as F1 dot delta R plus F2 dot delta R and etc. for all Fn's, right? Now I can take out all the F's outside and then dot it with delta R. As we discussed that the particle is in equilibrium, I can easily say that the summation of all the forces should add up to 0, which means the delta U comes out to be 0. So hence we have proved that the total virtual work by all the forces acting on the body or any virtual displacement is 0, provided the particle is at rest. Now guys, one more small idea before we move on to the problems. Imagine a rod, something like this, and let's say we displace this hinge point C by some distance, okay? Now if you draw the FBD of the rod AC, then there will be hinge reactions AX and AY. Forget about that. I want you to pay attention to this point C. So at this point C, the reaction forces are going to be CY and CX. So there will be some resultant force C that rod BC exerts on rod AC. So by Newton's third law, if I want to find out the force that rod AC exerts on rod BC, it's simply going to be minus C, right? So now if you displace this point C by some distance delta R or dr or whatever, you can see that if I take both of them as a system, the net force is C dot delta X minus C dot delta X. So that just computes as 0. So that's the reason why the net work done by internal hinge reactions all add up to 0. Okay, so now with that we can move on to the first problem. So this is the first situation that we are going to be solving. So in this question we have an external point load P acting over here. So the question is, you need to find a relation between P and Q, where Q is the reaction force on this block B by this wooden piece over here. So if this is the block B, the force Q is going to act in this direction. So this force Q and this force P, you guys have to find a relation for this. So that's the first question. So I hope you guys tried out the problem for a while. And also guys, initially the system is in equilibrium. Only in that situation you can apply the principle of virtual work. Okay guys, so the hinge reactions at these 3 points actually do no work because they are internal, right, as we just discussed in the previous page. So the only forces that we need to care about in this scenario, virtual work of this force P and this force Q. Okay guys, so now let's say the rod over here actually rotated by a small angle of d delta theta. Okay, so this is going to be the virtual displacement of the point C. This is very small. I just exaggerated the diagram. Okay, and similarly what will happen to this block is it'll get displaced in the forward direction by a small amount. Now let's mark down the names for it. Okay guys, so now for the point C over here, we only care about the vertical displacement of this point because the force itself is vertical, right? So F dot dr will only include the vertical component. So the work is simply force multiplied by the displacement in the direction of force. So let's say the vertical displacement of the point P is del yp. Similarly, this is the displacement of the block. Let's say this displacement is del yb. Okay, and obviously there is a force Q that is acting on this block. Now by applying the principle of virtual work, we can say that the net virtual work, which is going to be P times del yc, and it's positive work, right? So plus P times del yc, and Q is doing negative virtual work, as we can see. So this is going to be minus Q times del yb. This should both add up to 0. So now we have to kind of figure out what is del yc and what is del yb. I mean, I should have written del xb, right? Because its displacement is in the x direction. So let's just write it like that. So this is going to be del xb. So now let's figure this out. Now, in order to figure out the small virtual displacement, we are going to use the help of calculus. The y coordinate of the point C is going to be L cos theta, where this angle is given to be theta, right? So if I differentiate it, I'll get dyc, which also is del yc, is L sine theta d theta. Okay, so I'm just taking the modulus of it, minus L sine theta d theta, but we can take care of the signs ourselves. Okay, now similarly, the x coordinate of the point B, L sine theta plus L sine theta, that is 2L sine theta. So which implies del xb 2L cos theta d theta. So this is the del xb. So now all we have to do is substitute it back into our virtual work equation. Okay, so once we substitute the value of x del yc and del xb back into our equation, we simply get q equals p by 2 tan theta. Okay, so now let's move on to the next question. Okay guys, so the next problem is from Pathfinder, Newton's laws of motion, build your understanding, question 31. Okay, so the problem statement is that we have 2 long and 4 half as long light rods. So these are the long rods that they are talking about, and these are the small rods that they are talking about. They are hinged at their ends to form a pantograph consisting of 2 identical rhombi. The pantograph is suspended from the ceiling. The lowest hinge of the pantograph is connected to the hinge above by a light inextensible cord. Okay, so these two hinges are connected together by a string, and a load of mass m is suspended from the lowest hinge as shown in the figure. Find the tensile force developed in the connecting cords. So we have to find the tension force in this cord. Okay, so let's discuss this problem. Okay guys, so here also we'll use the method of virtual work. So firstly, as we discussed earlier, the hinge reactions at each of these points will do 0 work, right? For the virtual work, we only have to take care of work by mg and work by tension. Okay, so let's try to figure it out. So the tension force is acting at this hinge over here. Let's call it hinge 1, and it is also acting at this hinge over here, which is hinge 2. Okay, so let's just virtually displace our mass m by a small amount of delta 2. Okay, which basically means this hinge 2 is also moving down by the same amount of delta 2, right? So now we'll use the rigid body constraint. So let's say this is hinge 0. So the distance 0 1, if I say it is y, then the distance 0 2, by symmetry we can easily see that it is 2y, right? Del 2 is nothing but d of 2y, small change in this length 2y. So del 1, we can easily see that it is a small change in length y, which basically means it is delta 2 by 2. So if I displace this point 2 by a small amount, displacement of point 1 is actually half of that amount. Okay, so now we can write down the virtual work equation. So the virtual work due to the mg force is nothing but mg times del 2, and it's positive. So now we have to observe the tension force. So the tension force is acting at this point 1 as well as this point 2, and their magnitude is going to be the same because it's a light string. Okay guys, so by our rigid body constraint, we actually determined that this point 1, it goes down by an amount of del 2 by 2, and this point 2 goes down by an amount of del 2. So from here we can see that the work done by tension is going to be plus t times del 2 by 2 minus t times del 2. So that is nothing but minus t times del 2 by 2. And this should all add up to 0, which essentially means the tension T comes out to be 2 times of mg. So now some of you may have a question, if as the string is inextensible, if this point is moving by delta 2 by 2 and this point is moving by delta 2, isn't the string extending in this case? And the answer is, guys, as the displacements that we are taking is infinitesimally small. So it's as good as saying the string didn't even extend. For our analysis, we can just assume that the string length actually remained constant. So that's the answer to that. Even in this problem, the block B is not going to pierce through the wooden block. But still, as del xb is a very small quantity, we can assume some finite, microscopic displacement for the block B. And that's the reason why we can actually assume it. Okay guys, so now this is the homework problem over here. So we have an arrangement over here, something like this. And this length is L, this length is 2L, and we have two loads over here that are hung from the point G and the point O1. So in the problem, you guys have to figure out the ratio of G1 and G2. So solve this problem and comment down the answers below. I'll react to it if you get it right. And with that, if you enjoyed the video, guys, do like, share and subscribe. And that's it. Thanks for watching.